sell technologies across the board for drinking water and wastewater. We have a lot of installations in the state of Minnesota, particularly biosolids. We have plants at, we have dryers at SMSC, Mystic Lake, New Prague, Buffalo. So we're pretty familiar with the state. I'm here today to talk to you guys about thermal hydrolysis. It's new to the States. It's a newer technology. It's a cell lysing technology, which is a pre-treatment step for anaerobic digestion. What it does is, we'll go through in general. I'll kind of give you guys a background of good start, great start.
You want to see more of those fishing pictures?
All right, back again. Hi, my name is Bonkoski. I'm Kruger. What we're going to do today is we're going to go through an introduction of how thermal hydrolysis has come to pass and how the history of it, how our process specifically has evolved into what it is today. We're going to talk about some competitive cell lysing technologies, and then we're going to actually go through a plant that we have that has a plan to become an energy neutral facility by the year 2020. So one at a time, we're going to show you the development and then where we plan on being in the future of this technology. So to start, historically, treatment plants, this is kind of what you see today. This is a very basic outline of what we have, but essentially you have wastewater coming in, you bring in electricity and chemicals into a treatment plant, you treat what you have a waste product, which is sludge, and then you have effluent going out. This is kind of depending on whatever's within your black box here of your treatment plant. Pretty much the byproduct is the same. You always have sludge you have to get rid of, and there's always something you can do with it. In the States, generally, people normally just land apply these days, send it to a landfill, whatever you have. And as time goes on, sludge is going to be it's going to get much more difficult to get rid of your sludge, whether it's a Class B issue or just with what's in your product and the availability of land to get rid of it. Obviously, some of the states up here in the central U.S. don't have that issue yet because there's obviously plenty of land to get rid of it. But as time goes on, that's going to change. So what do we see today with sludge? You guys look at it as waste. It's a giant pile of waste, for better lack of words. And what do you do with it? Put it in a dumpster, you haul it off, you get rid of it, you never think about it again. Now, we don't look at it that way. We're starting to look at sludge as an energy provider. And the other resources that are available in the sludge are things that you can use across the board that many of you may have not thought of before. So what we look is, instead of looking at a wastewater treatment plant as that, we look at it as a biorefinery, because we see the products that we have, we see the potential for what kind of energy we can gain coming out of that process. So again, we have your resources coming in. Instead of calling it waste, we call it a resource because that's the fuel that we have to push through the biorefinery. We now have the availability to get clean water coming out. I don't know if you've heard the term toilet to tap, but that's becoming more readily known, especially in the U.S., especially in the Southwest, because we're running out of clean water. And overseas, I know in Asia, they're already doing it. They're taking wastewater, they're running it through a system, they're purifying it, and they're bottling it, and they're selling it back to the population of drinking water. So in the future, that's going to happen over here as well. And what we have here is we bring in energy, we bring in chemicals, because we have to use that to treat the water. But the way that we want to work this out is that from the biorefinery, we can actually generate electricity back and also generate heat that we can bring back into the cycle, thus making it more of a loop than an in and out. So instead of bringing in X amount of electricity, you can generate Y, and you can kind of come to common terms. Also, at the same time, you have all your waste, which the sludge, which you can now generate. There are a lot of options that you have where you can take the sludge and generate other things. Bioplastics are something that are new. You can actually take the organics that are left over in the sludge after the waste process, and the oils that are involved, you can actually use as an oil substitute in the creation of plastics. A lot of people are starting to look at that in ways for media, for aeration basins, and other things. I mean, the picture of a fork there, I don't think you would like to eat out of, like to eat dinner from a fork made from sludge. But at the same time, there are a lot of possibilities where you can get the oils out. A lot of plastics these days, plastic is used everywhere. You can use it. It has the same properties, and sometimes it's actually stronger than the plastic you would make use standard oil. Also reuse nutrients. One big thing that people are looking at is phosphorus removal out of the waste stream. phosphorus removed. The phosphorus can be used as a fertilizer. You can incorporate it into a lot of other, other fertilizers that you sell on the market. So there's definitely a market that's growing for phosphorus removal in waste. Okay, so that's kind of the overview of how we're going to look at a plant, in general. Today we're going to focus on thermal hydrolysis, which is a way to maximize energy production out of the sludge that you use in the wastewater process. So we're going to go through thermal hydrolysis in general. Essentially what thermal hydrolysis is the cracking of long-chain molecules in the sludge using temperature and pressure. As you can see, what that does is when you crack open the molecules, it makes all of the components that are inside of the molecules available for digestion much easier than they would in a standard conventional digester. This is just a very rudimentary drawing here, but you can see a molecule on the left. You add heat and pressure. Our systems technically run between 300 and 350 degrees Fahrenheit at 130, 100 to 160 psi. And then what that does is you cook the sludge, you break everything down, and then you digest it, and you'll see the benefits that we have. The pressure comes from progressive cavity pumps. That's a very easy way to generate the pressures we need, and the heat we get from steam. So there's a steam generator on site. You get steam, you inject it, you use the pressure, you cook it, and that's pretty much the process. Okay, so benefits of thermal hydrolysis. A lot of people see it as there's benefits across the board. There are really no negatives. Sorry, salesman is going to come out right now. So what we see in thermal hydrolysis is that you get increases across the board. Mainly, you get a huge increase in biogas production. With the plants that we have running, you can see almost a 40% increase in the biogas production that you're already having in the same digester. You also get a huge volume of solids reduction in your digester, reducing the volume of sludge you need to get rid of. The digestive capacity also increases because once you hydrolyze sludge, the properties change. Viscosity goes way down. It actually mixes more like water. So you have hydraulic issues or capacity issues in your digesters. The easy way to do that is if you have any kind of lysing technology up front, you can increase the capacity of your digesters without changing your mixing system or building more digesters. Also, sludge dewatability goes up. Since you have enhanced digestion, more of the organics are removed from the waste stream. So when you dewater on the back end, you get up to 7 or 8 percentage points on your dewatering using the same amount of polymers. The blends may change a little, but for the most part, it's the same go-to. Also, the volume of sludge for disposal goes way down. Obviously, if you're digesting more of the solids in your digesters, you have a lot less sludge to get rid of. You can see with different technologies, you can get up to 40–50% reduction in the volume of sludge you need to get rid of. Again, in Minnesota, that might not be a big issue these days, but getting rid of sludge is very easy. But in the future, 40% reduction in volume could be a huge cost saving for you. The other, obviously, biggest benefit here that I don't know if you can see it on the screen is that you get a Class A product. Class A is becoming a big issue for sludge around the country and around the world because once you have a Class A product, you can actually apply it anywhere. Class A biosolids are actually marketable these days. You can take it, you can dry it, you can sell it. And that would actually generate new revenue streams that you may have never seen before in your process. Okay, so I'll go a little bit through the history of how thermal hydrolysis came to light today. We are now working at thermal hydrolysis came around about 15 years ago. It started with a batch process, and this has been a very successful process. They've sold it overseas. Essentially, you operate, it's a batch process where you would essentially cook a batch of sludge one at a time using heat and pressure, and then take that sludge and put it into a digester. As you can see, this is a small flow diagram of how that would work. You bring your sludge in, and on the one side, you bring it in. We found that the best way to do it is you actually dewater up front, because the more water that you remove from the sludge before you hydrolyze it, the less energy you need to generate that. Because since you're injecting steam, you want it to react with the solids and not the water. So you bring a batch in. Batch comes in, 16% solids. As you can see, you fill up a reactor with sludge, you inject the steam, and then you create the pressure using pumps on either end. And then you cook this for relatively a half hour, and then you put it through a heat exchanger to cool it down, because obviously you're not going to put 300-degree sludge into a digester. So your heat exchanger here, there's a great option to recover all the heat off of the process, because you generated all the heat, you might as well try to keep it. As you take the heat, you cool it back down to, depending on whether you're running a mesophilic digester around 100 degrees or a thermophilic digester 130 degrees, you cool it down to where it is, you put it into a digester. once this is done, as you can see, you clean out the one, then you fill it back up with solids, and you do the same thing. So it's a batch process, it goes back and forth and back and forth. What you do then, you take all of the you take all the gas you generate, you bring it back to a steam generator, or you put it into, well, this is just the CHP unit. Valorization means the realization of capital. So anyway, you can, as you see, you have this biogas, which you can generate, power, electricity, or even funding, depending on what kind of system you have. If there are natural gas pipelines, you can actually scrub the gas, pump it right back into the natural gas pipeline, and you can get energy credits for it. So the key features of this process is that since you're hydrolyzing the sludge, you're getting a much higher concentration of dissolved solids in the indigestion process. That's great because, like I said, the volume reduction is humongous. The volume reduction is pretty significant depending on how your process works. You also get increasing waterability, so all those put together with the added benefits on both sides, you can see it's a great fit for a lot of plants. Now, looking at a batch thermal hydrolysis process, the big issue is that it's very costly. Capital cost is high, O&M costs are high, everything is just very expensive. There are a lot of benefits to it, but some of them don't outweigh each other because it's so expensive. As you can see with the batch process, first of all, this is the footprint of about a 20 MGD plant. You can see that's just one piece of a pre-treatment step for anaerobic digestion. It's a very large process. So the feeding pumps, you can see the average flow is much higher since you're running in a batch. The circuits you have, all the piping, are much higher. The flows are much higher, much larger pipes, much larger valves, instrumentation, everything. Even the steam injection. Since you're heating from room temperature up to 350 degrees if you need, you're really using a lot of steam to get up to that temperature. Also, the boiler you have to generate the steam is much larger. And you even have, again, more valves and instrumentation to run this larger process. The consequences, I think I just mentioned a couple of them. The investment cost is very, very high. A lot of pipes, a lot of materials, a lot of O&M. O&M costs are high. And also, you're underutilizing your equipment. There's a lot of losses associated with running a batch process. Since you're heating something up and cooling it down, and heating it up and cooling it down, there are a lot of issues where you're losing the energy, and that's not really the idea of what we want to do. So, shifting to a continuous thermal hydrolysis process. This has kind of been the development of where we're moving these days. Moving into a continuous system, you can see, for one, it significantly reduces the footprint of the system. It reduces the investment cost. We'll get into the details, but the system is a fraction of the size of a batch process. You really improve the efficiency of your process since you're not losing the heat that I just briefly discussed a minute ago. And also the operation is much simpler since it's not a batch process. They actually operate as a plug flow reactor. So it's a single pass through and everything's moving through consistently, and it doesn't, there's no on off, it gets up and running and it stays where it is. So the basic concept of a continuous system is that it's a continuously fed reactor. I hope that would be self-explanatory. And also the benefit of running a continuous system is that you get a higher percent of dry solids going into, tell them I said hi. I don't know. The higher solids, you get a much higher solids concentration coming into the system. What we found with our batch is that since you dewater up front, you really can't get above 60% solids, which kind of puts a limitation on the system. With a continuously fed reactor, you can go, we would like to see 20% solids, but you can actually get as high as 25, 30%. And I'm not saying that's feasible off of the standard process, but the higher percent solids, the better, because again, the less water, less energy you'll need to hydrolyze the sludge. And again, what we found operating-wise, going from a batch process to a continuous process, is that the conditions are still the same. You still need roughly 30 minutes, you still need the same pressure, same temperature to run the process, and you get the same results. So we've taken a very large system and made it much smaller, and you get the same results, which is really exactly what you're looking for. So I'm going to talk to you briefly about our Hydrolysis system. Hydrolysis is a product that Kruger sells. That's part of the reason why we're here. This is the continuous system that was developed from the batch system that used to be around. So this continuous system, again, really reduces the investment cost. As you can see, the plant here on the side, I'll get into detail, but this facility is a 5 MGD plant, and the reactor itself is only a 14-inch pipe. It's about 40 feet long. So the size of the system, the footprint, is very, very small. It's very compact. It's very easy to use, and you get the great benefits out of it. So essentially, with the smaller system, I think we covered these. The system is very energy efficient. With the higher solids composition proceeding capability, what you have is you reduce your heating requirements significantly because you heat up to 350 degrees. You maintain a constant temperature throughout. Most of the pictures I have here show the system bare bones because I want to show you the internals of the system. Now everything is heat traced and wrapped, and you can't see anything. It's just a big shiny ball of pipe. So let's move into the process. I'll kind of tell you guys specifically how this system works, and then we'll get into how some other systems work as well. The thermal hydrolysis process is actually pretty simple. You'll see that there aren't a lot of, this is a proprietary technology, but at the same time, the principles are there and they're used in a lot of different ways. The way the system works is starting from one end to the other. You have your sludge, so your treatment plant would be over on this side of the system. If you have anaerobic digesters, obviously that's what we're here. The digesters are on the back end. You dewater the sludge as best you can. I mean, it says 25% on here, but that's, hopefully, I guess thinking that you can do the best you can. 20% is fine, but this is the lower percent solids you have, the more water you need, the more energy it takes. Still, it's kind of a marginal offshoot, so that's the way it is. You have progressive cavity pumps up front. You pump your sludge into what we call a static mixer here. It's essentially just a vertical section of pipe with a static screw inside. What we do is we inject the steam through a few injection ports in the bottom, and it actually it mixes with the sludge and heats it up to the temperature we need as it goes through the mixer before it goes into the reactor. And once we go into the reactor, it sits there for 20 to 30 minutes and hydrolyzes. So it essentially cooks as it goes through the reactor. Now, after you sit through the 30-minute time on the back end here, you now have hydrolyzed sludge that's at 350 degrees. So the one way the system shows its efficiency is that we recover all of the heat off the process that we can. The best way to do that is with heat exchangers. So we have a couple different options for what we do. We obviously are generating steam for the process. What we do first is we take all the heat that we can and send it through the water loop through the heat exchanger over to the steam generator. Because obviously if you have water at 150 degrees versus 100 degrees, it's going to take a lot less energy to hydrolyze or to generate steam than it would if you were using room temperature water. And then on top of that, we have an additional heat exchanger, which we can use for energy recovery depending on where we need it. Some facilities, they have hot water heating loops on site. They'll use that to heat the water to go through the buildings. Or you can use this to also heat your digesters, or wherever you would need another heat source on site, the heat is available. So if you follow the percent solids coming through the process, we come in as high as we can. We'll just say for example it's 25%. After you add the steam, it comes down to roughly 20% because you're adding water to the process. Now after it goes through this step, it's still at 20%. We actually have to rewater the sludge before we put it into a digester, because hydrolyzed sludge, the viscosity is much higher, but you still can't mix it in a digester at 20% solids. So we use dilution water, depending on the driver for your facility. This could be potable water or effluent or anything else. It just really depends on how your system is set up to run. We'll go through some of the options and why this would be different as we go. So what we see then is that a standard anaerobic digester runs 4 or 5% solids. After you hydrolyze sludge in any shape or form, you can run it at a much higher percentage. We regularly run our digesters at 10 to 12% solids, which is fantastic. So we've actually doubled the capacity of our digester without making any changes to the digesters alone. So the retention time goes from say 20 days to 40 days, but you're running it at 8% solids instead of 4, or 8 to 10% solids instead of 4, and that really just it increases your capacity. It doubles your capacity. So there's a few different options for how you can actually use, say, a thermal hydrolysis system within your plant. There's 2 configurations. The first one is we call an LD configuration, where you do your hydrolyzation and then you digest. What that does is, depending on your plant, you have a combination of primary and secondary sludge. You hydrolyze it and then you digest it. I mean, depending on if a facility is already existing and they only have one digester, there's ways you can fit it in. The biggest benefit to hydrolyzing sludge is on secondary sludge. If you have primary sludge, it readily digests itself. So if you have a plant that has just primary sludge and you have anaerobic digesters, then hydrolyzation might not be the thing for you, because you're going to digest everything you can anyway. The way that it works is that on a lag stream is really where you've already had some kind of reduction biologically before you want to break up all the cells before you can want to digest it to make sure you get the benefit out of the sludge you can. So in this situation, you run, as you can see, the Xless unit itself stays the same. Whatever configuration you have, the nuts and bolts are always there. You always have steam condenser, reactor, heat exchangers, and then you rewater, and then you put it into a digester. As you can see, you take the biogas off, you can double the capacity of your digester, you can use the gas to run your steam generator, or you can run it to a CHP unit. Again, the idea of this process is to recover all of the energy you can off of the process. So you don't want to waste anything. If you're running a system and then you're flaring your gas, it's really not what you want to be doing. Obviously, you have to flare every now and then, but the idea is to generate as much electricity as you can. Again, final dewatering at the end, you're going to get percentage points higher. If you're roughly getting 25%, you're going to see much better results, up to 30-35%. We'll show you some operating data from a plant that we have. So the other configuration we have for this process is the DLD process, where you actually digest first, then you use the Xless and the hydrolyzation, and then you digest again. Now the benefit of this is that if you have a large stream of primary sludge coming in, or a mixture of primary and secondary, the primary sludge is easily digestible. So the benefit of this system is that you're going to get the benefits of a standard digester up front. You're going to get the volume reduction that you can out of the process here. So you're going to reduce the volume of the sludge here, and then it's going to make this system smaller. So what you would normally get out of the process, you digest it, and then you hydrolyze it, and then you digest again, because you've opened up all that additional the carbon compounds that you would have not digested originally that you can get a second time. So what we've seen is that this is the most productive way to thermally, or to hydrolyze sludge if you're doing it at a plant where you have the capacity to set up a configuration that is the DLD. As you can see here, with this, one thing they do here is that the plant that we run in Denmark, they actually have, we'll get into detail, but they take all the heat off the back end. Again, they take the heat first and they heat up the steam, the water going to the steam generator, but they take all the heat here. They run a thermophilic digester up front, mesophilic digester up back. They take all the heat off the process, and they have more than enough heat to keep the feed coming into the digester to keep this at the temperature they need. So they actually reduce their need for heating their first digester because they have the heat available through the process. So that's thermal hydrolysis in a nutshell. What I'm going to do is talk to you about a couple other cell lysing technologies just to show you there's a lot of other options out there where people are taking the same principle but applying it in different ways. Canby, they have a thermal hydrolysis process. They've actually been very successful in selling that overseas. It's actually pretty much the same thing that I talked about front, which is a batch thermal hydrolysis process. They've made some changes to make theirs as energy efficient as possible. And with these systems, this is actually a picture of the Canby plant here on the right, and this is a schematic of one. They are much larger, but what they do is they target larger processes. So I don't know if you've heard of the DC WASA job down in Washington, DC. They won a project there, and it's a 500 MGD wastewater plant, something like that. It's enormous. So their process, they found ways to make it actually work on a much larger scale. And that's kind of, it's a huge market, and that's what everyone's looking for. Other cell lysing technologies, this is a technology called OpenCell. This is not a thermal hydrolysis process. It's called focused pulse technology, where they actually take a stream. So if this is, this is kind of a rudimentary drawing here, but if this is your sludge stream, they take a side stream and they run it through this system, which actually has a series of electrodes, which essentially hydrolyzes the sludge by using positive negative to disrupt the molecules and break the cell walls down. This is kind of a single pass, and it significantly does enhance biogas production. You get increased digestion the same. But this system obviously goes in at a much smaller scale, and it's much more affordable for people who may have smaller streams or different ways or different goals for what they're looking to gain out of their digestion process. Another system is the Vogelsang process. It's called biocrack disintegration. This is actually an electrokinetic disintegration. It's kind of the same as it's very close to the OpenCell technology, but this one, again, as you can see, what they do here is they have an electrode that goes into the pipe that the sludge passes through. So what this does is as the sludge passes through, it breaks the cell walls down as it goes on. This system's great in the sense that it's very portable and compact. You can actually get these, I don't want to say off the shelf, but they're very readily available. So if you have a stream going into your digestion, you can insert this pretty quickly. These electrodes are pretty easily serviceable. So very low capital cost. You put this in, you're going to get increased digestion pretty much right away. These systems don't create a Class A product, but however, a lot of people don't need that, so this is a way to get the enhanced digestion you're looking for on a lower capital cost. Okay, so what I want to do now is I'm going to give you guys a pretty in-depth description of the first full-scale facility that Hydrolysis was installed in. It's in Hillerød, Denmark. The technology, I don't know if you guys know, most technologies we have all come from Europe anyway. There's an office, a Kruger office in Denmark. This is right next to it. We set up an Hydrolysis system, full-scale system. As you can see, it's a 5.5 MGD facility. It's not fully loaded right now. It's running around 4 MGD. We've had this plant online for the Hydrolysis system online for almost 2 years. So we have some pretty good operational data, and they've allowed us to really run the system any way we wanted to make sure that, in every different scenario, since this was the first system of its kind. On the water side, this is just the water treatment line to get you guys to know what's going on. They have biological nitrogen removals. They have 3 mm screens, grit and grease, primary sedimentation tanks, an activated sludge plant for nitrogen and phosphorus removal, final clarifiers, hydrotech disc filters, and then they also have chemical phosphorus removal on the back end. This is just the water process. That's not really what I'm focusing on today. Just wanted to show you what they have on the plant. The waste side, so what they have is they have a combination of primary and secondary waste. The primary waste, they just thicken by gravity, so they have it, they put it in sludge beds, let it dry out a little bit before they bring it out and put it into the Hydrolysis line. Their secondary, they thicken mechanically using a draining table. So they bring it in, it comes in roughly about 5 or 6% when the two are combined together, and then they dewater up front using a centrifuge, and then they put it into the Hydrolysis process. Before we ran the Hydrolysis system, they were set up with 2 digesters. They ran them both in series. They both ran thermophilically. As you can see, they ran about 131 degrees Fahrenheit with no parentheses on the back end. And the 2 digesters are slightly different in size. As you can see, one is about 53,000 cubic feet. The other one is roughly 33,000 cubic feet. And like I said, they ran them in series, so they had a smaller one, they built a larger one as time went on. This plant was originally built in the 60s. So over that time, there were not a lot of significant upgrades, and we're going to get into how they're going to make it themselves and then use the facility as we move on. So pre-installation of the Hydrolysis system. As I said, this was our first facility. We put it in as a demonstration unit, so you're going to see a lot of containers. This is not what a permanent installation would look like. However, we are building a permanent installation on site for them now. So going back, this is pre-installation. As you can see, nothing's hooked up yet. I wanted to show you the size. It's a 4 MGD plant. Obviously, that doesn't completely correlate with the solids loading, depending on your facility, but this shows kind of the sizing of what we have here. This is the static mixer column here. As you can see, there's just a flange with a static screw inside. The steam comes down from the steam injector into this port, and they hook up through these nozzles here, and then the steam is injected through 6 nozzles, and it pushes the sludge up and hydrolyzes it as it goes up through the static mixer. As you can see over here, this is the reactor column itself. So it goes out of the static mixer into the reactor, and then goes along the reactor tube, which is 40 feet long, which you can actually also see right here. So this is the bulk of the process. The footprint is very, very small. What they've also done, the heat exchangers that we described that heat the water going to the steam generator, and also heat up or you can take the heat for wherever else you need. There are 2 heat exchangers that run the length of the reactor just above it. So what you do is, again, footprint concerns, this is the best way to transfer the heat in the smallest amount of space. Again, as you can see currently, they have the whole system is heat traced, which is great. It's in Denmark. I don't know if you've ever been there, but it's freezing cold 6 months out of the year, very much like Minnesota, except not this week, I guess. But everything's heat traced, insulated outside, so you don't need a structure around it, you don't need a building. Since you have the vertical tube here for where the static mixer is, the Hydrolysis system sits about 8 feet off the ground, and with our permanent designs, all of the solids handling equipment and whatnot all goes directly underneath it, so you can put this whole system in a 40 by 40 area with no problems whatsoever. As you can see here, this is what the hydrolyzed sludge looks like. I don't know if you guys can see this that well, but this is out of digester 2. This is at 10% solids. As you can see, this looks like a milkshake. It mixes very well. There's no issue. They've doubled the capacity of their digesters, again, without changing in their mixing or any of the other operating parameters of the digester. So, as you can see, we hydrolyze. Once you pump it in, it mixes very well, and it's actually, there's no settling because it's just completely macerated. There's really nothing to settle, so it stays in that form very, very well. Here's some of the data from the facility before the plant went online, and then it went online around October 2010, so it's been online just over a year and a half. And then we waited about 6 months to start taking data, and we'll show you how the performance increased through the digesters after the Exodus went online. As you can see, here was the average load, about 10,000 pounds of dry solid per day. They were running thermophilic digestion in both digesters for 25 days. As you move over to the Exodus system, as you can see, we ran the DLD configuration. So they ran everything through the one digester and got the reduction they needed, and then they ran Exodus and hydrolyzed the sludge and then digested again. As of February 2011, you can see the loading was the same. They actually lowered the retention time in the first digester because they found that they were getting 80% of what happens in the digester is getting through the cell wall. So the easily biodegradable stuff, they found they could get that benefit in a shorter period of time and then run it through the other digester. They also used a smaller digester up front to make sure that they had what they needed. The second digester, as you can see, they were running mesophilically for 15 days, and after they hydrolyzed, they got an additional 30% COD solubilization in their digesters. So they went from 25 days to an overall 27 days up front, and they increased their retention time a little bit, but at the same time, you'll see the benefits here in a minute. Again, as you can see, the loading went up significantly in May, and they're still getting roughly the same results as they were getting when the loading was lower, showing that even through operational flexibility, the system performs very, very well. Here's some of the data that we'll look at here. This is the solids destruction within the digester. Before the Exodus, you can see they were getting roughly 33% solids destruction in the digester. Once it went online, it went up to 45 to 47%, which is roughly a 36 to 42% increase in the solids destruction within your digester, which is pretty significant. Again, biogas production, which I would imagine in the U.S. is one of the larger drivers for putting this in. As you biogas, you obviously want to put in a CHP unit, do what you can. As you can see, they were their biogas production went up almost 25 to 30% over the 6 months that it was operating. So if you get a 25% increase in your biogas, that really benefits you if you're trying to run a CHP system and reduce the energy or increase your energy production on site. Again, final sludge composition. This has to do with the dewatability of the sludge. Before the Exodus system went online, they were getting 25% solids. On the back end, they were using a plate and frame press for their solids, and they were getting consistent 25%. After they started hydrolyzing the sludge, they went up 7 percentage points with their dewater. And one of the main drivers for this process in Denmark was the cost of their sludge. They shipped everything off to an incinerator because obviously the population overseas, there's not a lot of room for people to land apply solids, so everything gets taken somewhere. They were paying over $200 a ton to dispose of their solids for an incinerator. So getting this increase here in their final sludge composition and also reducing their sludge volume has really made it possible for them. They've seen significant savings in just getting rid of the sludge by itself. They're getting almost a 35 to 40% reduction in the sheer volume of sludge they have to get rid of, which is very significant in the sense when you're paying that much money to get rid of your sludge. So the Hillrod facility, they agreed to put this Exodus system in because they have a goal to become energy neutral by the year 2020. They actually publicly announced this, so everyone in Europe is watching to make sure that they're going to do this properly. So they kind of developed, they did all the front end research and figured out what they needed to do to make sure that they could make an energy neutral facility. They currently consume roughly 200 megawatt hours per year at their facility. And they also have plans to increase their capacity by 30% over the next, well, I guess it's 8 years now. This data was 2 years old, that's why we put the system in 2 years ago. They also overseas, a lot of people pay, a big factor is CO2 emissions, and they're looking to reduce their CO2 emissions guaranteed by 2% every year, if not more. And also, so what they did is they took their plant, they broke it down, and they focused on 2 areas as to how they could become an energy neutral facility by the year 2020. The first one is optimizing the process. We'll go to this detail, but they essentially know that they're wasting energy in different parts of the plant, and they need to figure out how to fix that and how to make it move forward. And also energy production. They know with adding a system like Hyrdolysis, they can generate more biogas. They can use that in a gas engine and then generate their own electricity. So what they did for energy optimization, they took their facility, they broke everything down to figure out where they were using all their energy. What they found that their biological treatment was using 60% of the energy was going to their biological treatment. That's a pretty large piece of that pie. Also on the other side, in sludge treatment and dewatering, you see their 20%. The primary up front, with their screening and whatnot, was roughly 12.5%. Pre-treatment, again, 7.5%. And then obviously there's just a sliver of miscellaneous in there to show you, some other energy costs that are occurring on site that were out of the process. But obviously the big red one is the one you want to look at and focus on because that's where you can make the most savings. So optimizing the energy. What they said, they developed a process here where they looked at, okay, since our biological treatment is using all of this energy, what can we do? The first thing they did is they installed new blowers with VFDs. They were running old blowers that were just on and off, and they installed new instrumentation, new DO probes to make sure that they're getting the right amount of oxygen depending on the right amount of oxygen. The right amount of oxygen depending on the season and loading in the facility. So just by installing these turbo blowers and instrumentation, they actually cut down their energy consumption significantly right away. They also have done a complete control system upgrade on site. People think that's very simple, but you essentially put intelligent online controls in to monitor those DO probes and make sure that everything is running the way that they need to, so they can really optimize the processes the way that they can. Live trending, and all the operators can now see what they can from home, so when the guys are on call at night, they can monitor facilities remotely. Also the local engineer that runs the plant, they monitor as well to make sure that they're optimizing everywhere they can. They also did complete SCADA upgrades because again, this plant was built in the 60s. They still had chart recorders, which I'm sure a few of you guys probably have those in your plants as well. But you're looking at pinwheels and you take them every day, you put them in a cabinet, you never look at them. So getting everything online, available through the internet is a great way to make sure that you're keeping everything on track and where you want to be. Another thing that they actually have done is for optimizing their energy, they're installing something called the Anitamox process. This is an MVVR that they're actually using on the centrate that comes off of the dewatering equipment. What this does is that you can see with the Hyrdolysis, people ask a lot, since you have the ammonia or do you have increased ammonia levels with the process since you're hydrolyzing the sludge? The answer is not really, because most of the ammonia comes out with the sludge as it goes off site. What you do, since you digest possibly 2 times, you're going to have more ammonia you need to treat on the back end. Now, when you send that to the front end of your process, it's going to make everything more energy. You're going to consume more energy trying to treat that nitrogen through your standard process. So what they've done is they're going to put this system on the back end. It's an MVVR. It's a single pass process where you just essentially fill up tanks with the media. It comes pre-seeded with the proper bacteria, and you just run it through. You get a 90% reduction in the ammonia levels. You also get a 75 to 85% reduction in the nitrogen limits, or in the nitrogen coming back to the front end of the plant, which just really helps not put an additional load on your facility since you've added new processes. Again, they've also put the Hyrdolysis DLD system in here, so they can, so on the energy production side, you can see that they're producing more biogas. They're generating electricity using a new gas engine they installed. They're also using the heat off of the process to heat their digester up front, reducing their energy consumption, and also using it to heat the steam to minimize the energy that they need to generate to run this system. They used to run both digesters thermophilically. They found that if they only run the first one thermophilically, they can run the second one mesophilically and still get the same process. So they actually have they need less energy to keep this hot. Obviously the sludge coming in is hot enough, so they actually need no energy to heat the second digester whatsoever. So again, they took 4 steps. I don't know if you guys can all see this very well, but this is is a pretty crude PFD or flow diagram of the system. So they took 4 steps. They're optimizing their aeration system, which is in here. They're installing new blowers and VFDs and monitoring equipment. They installed the Hydrolysis and CHP unit down here, where they have the Hydrolysis system, and then they're running out. And then, as you can see, they have a reduction in the sludge they need to get rid of, which is their main driver for installing the system. Intelligent online controls, which kind of encompasses the whole thing, where they have real-time monitoring for every process on site now, where they can make sure that they're doing what they're doing correctly. And they also put in a reject water treatment, which is just our the EMOX system, which is treating their sanitary coming back to the front end. So here's just an energy breakout of where they plan to be by the year 2020. What we're talking about right now, they've already put the new blowers in. The Hydrolysis system is online. It's been online a year and a half, but again, it was a demonstration facility, so it'll be going down later this year, and as the permanent system comes online, and also with the SCADA upgrade system, the SCADA upgrades, they're working on that as well. But obviously, they have a goal to get all of this accomplished over the next 8 years. So it's not all going to happen in 2 weeks. It's going to take a little bit of time. As you can see, these are the conditions they were seeing before any of the process was made. So they're roughly using 200 megawatt hours a year of energy every day. The effect of measure 1, which is installing the new blowers with the VFDs, they're actually going to cut their energy consumption almost in half just by that. As you can see, optimizing your optimizing your biological treatment really cut their energy consumption in just about half. The effective measures of 1 and 2, this is with the new blowers and also with the Hydrolysis system going online. So what's this showing is once Hydrolysis is on, there's obviously an added energy consumption here, but at the same time, you're now generating all of this power from the gas and from the gas that you're generating in the process. So effects of measure 1, 2, and 3, as you can see, once you go from here, once you get the smart online controls, you optimize your system further, you can actually, you lower your energy consumption here because you're optimizing all your processes, and you're also generating even more gas because again, once you optimize the process, you can really make sure you pull all the energy out that you need. And then again, the effects of measures 1 through 4, once you put the ANITA process online, and you reduce on the back end, you can actually, again, generate more power. So what does this show you? Not only does this become an energy neutral facility, but you actually can become an energy producing facility where you're actually generating more energy than you need. And that is a huge accomplishment for any facility because obviously you're now generating more power than you consume. So you go into a whole other realm of what do you do with the extra power? It's a horrible problem to have. As you can see, overall, what they're going to do is they're actually going to sell the registration rights to the power that they have and back to the grid. So what they're going to do is they're actually be making money off the extra energy that they sell. So their goal by the year 2020 is to become an energy neutral facility, and obviously in even an energy producing facility. Now these are characters that we are obviously not true yet. These are all assumptions and hopefully well calculated to the fact that they will be an energy producing facility by the year 2020. On top of that, they're also going to increase their hydraulic capacity by 30%, which means they're going to be able to accommodate the growth in the area for years to come. The biggest numbers here is that just by installing these processes, they're going to reduce their annual operating costs by almost $600,000 a year. Now that's a pretty significant chunk of change. And you ask, they also reduce their carbon footprint by almost 350 tons of CO2 equivalent per year, which is a 50% reduction in their carbon footprint, which means, carbon footprint is something that everyone's starting to bring into light nowadays, and it talks about it's just the overall footprint of your plant, meaning every resource you get, where it comes from, what it takes to make it, where you have it, and how you get it to site and how you use it and dispose of it. So it's kind of like the life cycle of your plant, looking outside the walls of your facility. Now, reducing that carbon footprint by 50% is not only great for the environment, but it's a big accomplishment to do something like that as well. Again, they're going to sell the registration rights for the energy that they're going to generate. So the biggest thing is that what's the total investment that they're going to, obviously the bottom line is how much is this all going to cost me. The total investment that they're going to invest is roughly $4.5 to $5 million US over the next 10 years. And if they were to pay all that in one time, the payback would be roughly 10 years because they're going to save $600,000 a year. Their operating costs are going to go down. So as you can see, if they invest $5 million, it's going to take almost 10 years to get it back. As they're doing this step by step, the payback is actually going to be a little bit less, assuming that once the Hydrolysis goes online, they're going to get more of that energy back as soon as they can. So this is kind of this is what it looks at in a nutshell. So essentially, they're going to invest $4.5 to $5 million on a plant that's 50 years old upgrade the entire system, make it not only an energy neutral, but maybe an energy producing facility in, you know, in less than 10 years. So just to do a quick recap on where we started here today and kind of the theme of what we wanted to do is, you know, I think the energy neutral information is very, very important, but we look at it as one of the cornerstones is putting in a thermal hydrolysis process. Really the benefits are shown across the board. You have, again, it's a continuous process. Your operating costs are much lower. It's very reliable. There are not many moving parts. I don't know if you guys can tell, but I mean, it's just, there's a pump, a couple of pumps and some instrumentation, and it just pumps through. There's literally almost no valves you need to use. Very simple system. Or I should say all of the lysing technologies are very simple because they all have one common goal, and that's just to improve that jet. Again, you can get a Class A biosolid, which is very important for some, maybe not important for other. Again, with the two configurations we have, there are different situations where if you don't need a Class A biosolid, you can actually bypass all of your primary waste and put it right in the digester and just hydrolyze the secondary waste to make your system even that much smaller. Again, enhanced digestion. I think, you know, the benefits, I've said probably 100 times, that's kind of the idea. You get increased biogas production, you get sludge reduction. On the back end, you get increased destruction in your digesters, and also your dewatability goes up. So you kind of see benefits across the board. And with this process, the amount of energy that you can produce actually makes it pretty much a self-sustaining process. So your energy consumption on site pretty much doesn't change if you know how, if you properly handle the resources that you have available through these processes. And then again, the DOD configuration, we're looking at it as a cornerstone for the future of energy neutral facilities. So, you know, this is the best way to maximize the resources that you have out of the sludge that you have in your system, and this is what we see is one of the best ways to make sure that you can make your system self-sufficient. So that's pretty much the bulk of what I have. I feel like I covered a lot over the last 45 minutes, so does anyone have any questions?